this work, I would say this is a sort of outside of my normal theme of work. This is going to be a very non-technical talk in a lot of ways, but it stems from my sort of longstanding interest in making optimization and data science, data-driven decision-making more generally, accessible to as broad a public as possible. And I think that the new tools in artificial intelligence, particularly large language models, are really going to be transformative in bringing optimization to a wider audience. So I would say this project is really an exploration of what's possible in terms of an optimization modeling interface that will then widen the scope of the kinds of problems that we can attack as, optimizers, numerical analysts, data scientists. Okay, so this is really about AI and the future of optimization, and it's joint work with two of my students at Stanford, Aliad Mahdi-Tashnizi and Wenzi Gao. Okay, so here's the challenge. As an optimizer, I think one of the things that drew me to optimization is the potential to really accelerate and improve efficiency in almost any problem domain. I thought it's very exciting that we have the potential to improve almost anything, right? Applications from energy, designing a smart grid that really efficiently uses our resources, to routing problems, let's say routing the trucks for UPS, FedEx, or Amazon in order to deliver as many packages with as little, pollution as possible, scheduling airlines, making sure that the flights are on time, even in the presence of sort of disruptions to the network. Or supply chain problems. How do you manage an efficient supply chain and reduce the cost of your logistics while being able to, or the size of your inventory while being able to deliver goods to at the time that you need them. Okay, so all of these, domains give rise to very large-scale optimization problems, generally modeled as mixed integer linear programming problems. You'd expect to see in each of these domains really large operations research teams working to solve these problems because they're a huge sort of cost and a sort of critical aspect of businesses in each of these areas. And this is just a small sampling of the areas where optimization is used. Okay, but one thing that always, sort of bothers me, as I think about applications of optimization is in order to have an optimization modeling team, optimization team, an OR team, you need to be able to, the enterprise needs to be able to afford to hire the OR team, which means the savings due to better optimization has to be greater than the salary of the optimizer, right? At the very, very least, right? So that means it's really only something that's accessible to the most large businesses, right? To, businesses that are bringing in maybe hundreds of millions of dollars in revenue every year. And that really restricts the domain, right? There's lots of smaller problems, and there's many, many, many smaller problems, right, that are generating a lot of waste in our economy. And there's also lots of interesting problems, right, with interesting new, structure that optimizers might enjoy. But it's very hard to sort of get access to that, right? Solving a problem is modeling the problem and using an algorithm to solve. And kind of surprisingly, given the emphasis in, academic optimization, we concentrate much more on how to develop good algorithms for solving. This is true for me as well in my own research in my lab, right? Whereas, out in industry, the modeling is the primary bottleneck. It's usually not, the problem is not that the solver can't solve the problem. The problem is that you don't even know how to pose the problem. Okay, so let's think about what large language models and sort of AI more generally can do for, bringing optimization to a broader audience, democratizing it. And we're going to focus on mixed integer linear programming in this talk, just because it's easier to say something concrete in a more restricted domain. But mixed integer linear programming probably is the optimization technology that's powering the majority of the savings in sort of operations sort of in businesses throughout the economy. Okay, so here's an example of the kind of problem we're thinking of, okay? This is a pricing problem that we've been talking to lots of companies to say, what kinds of operations problems are you solving? This is one that came from the largest fashion retailer in the world, okay? So the global fashion brand sells articles of clothing in many markets. We can estimate how price changes affect sales for each article, assuming constant price elasticity. Maybe we've got estimates of the elasticity. The price changes have to be in multiples of €1. Initial prices for each article are given. No more than 20% of the prices can change at a time just because of, sort of stability that's required, to keep the customers happy. Each article has a maximum production volume. And then given sales forecasts for every article for the next 12 months and past elasticities, you want to choose new prices for each article to maximize the expected revenue. Okay, so this is the kind of thing you can imagine like a business leader formulating this kind of description of what they're trying to do. Okay, you cannot imagine a business leader formulating this kind of description of what they're trying to do. Okay, this is code in Gurobi Pi. So this is Python code, and it's the interface to Gurobi, which is one of the most powerful mixed integer linear programming solvers available right now. Okay, so this is a translation of the problem on the previous page into code, right? You've got variables like the price change, the quantity sold, the indicator function of whether the price changed, some multiplier, but this is, it's pretty complex. I would say that the translation from the previous page to this page is non-trivial, and this is exactly the kind of thing that your OR team would be in charge of. They'd be in charge of building this model, maintaining this model. Now, once you have this model, right, this is not a solution. This is not the values of the prices that you should have, right? But this is code that produces a solution, right, given problem data, given the elasticities, given the demand forecasts. Okay, so this is the problem that we're going to think about tackling with a large language model, moving from this natural language description to solver code, which can be translated into, the ABC of a standard form mixed integer linear program, and then solved to optimality using existing solvers. Okay, so we're not going to think about that part. We're going to say, we know that these solvers work. They actually work quite well at large scale. The problem is modeling. We're going to concentrate on the modeling. Okay. The problem clear? Any questions? Okay. Okay. So, yeah, the big picture again, the solvers are really reliable. The modeling requires expert knowledge. So right now you've got the operations research expert thinking very hard about this modeling, and we want to automate it. Now, what would that entail? What would that entail to model using large language models? Okay, it involves understanding the complex business logic expressed in natural language. It involves some mathematical reasoning, okay, in order to translate these business concepts into linear constraints. And there are a bunch of tricks that are used for this. Things like big M relaxations. Do you guys know big M? Not everyone knows big M relaxations. Many people do, but not everyone does. This is to say, you can only allow the price to change if this indicator variable is true. Okay. So, and then you can count up all the indicator variables that are true, that are 1. That tells you how many of the prices changed. And then you can put a constraint on that in order to ensure that no more than 20% of the prices changed. Okay. So there's some trick to make sure that the prices only changes if that indicator variable is 1 and not 0, which is called a big M relaxation. So there's some, there's some sort of tricks that are important to know. And then there's implementing solver code. So for example, knowing what the Gurobi Pi interface, what functions it has in it and how to use those functions. Okay. So can a large language model like ChatGPT help? So ChatGPT is now doing the hard work of formulating, and the analyst gets to sleep. Okay. So there's, there's one obvious approach you should try even before this. You say, well, maybe we don't even need solvers anymore, right? Maybe we're all totally out of work. Because we can just take the problem, write it down, give the whole thing to the large language model and have the large language model, either write the code to produce the solution or maybe even emit the solution directly, right? Ask the large language model to produce the numerical solution, right? So we could ask it to produce code for the solution or the numerical solution given the entire problem. There are, reasons to expect that there are good things and bad things about that. The good thing is that it's very easy, right? All you have to do is tell your problem to the LLM and something comes out and it answers you. It does answer you. It doesn't refuse to answer this kind of question. The bad news is that it's very unreliable. And that's because of sort of many reasons. You should not expect this to work, particularly for large scale problems. The reason you shouldn't expect it to work is a large language model, you really should, this is just a statistical learning technique, right? The way that these models are trained is just next word prediction or leave one out prediction. Okay, so from a string of tokens, it predicts the next token. From a string of tokens, it predicts the next token. Okay, so if it's seen stuff like this before, then it's pretty good at predicting the next token. And maybe if it's seen your problem before or something very similar to your problem, then it could predict the next token, which is the answer. Okay, so sure. Like if your problem is small, simple, then it's something that you could expect that it could have appeared in the training set, or something very like it might have appeared in the training set. And then maybe a direct solution like this could actually work. But so for sufficiently large optimization models, these are right. I mean, there's a reason why we're solving them with, complex solvers. We can't do it with pattern matching. We can't do it with like k-nearest neighbors or something like this, right? Even in the appropriate embedded high-dimensional space. And that's because the interdependencies of the outcome on the problem data are highly nonlinear and complex, and but they're also like deterministic, right? They're governed by real rules. There's a reason why we really believe that solvers are the right way to go. The solutions involve things like matrix inverses, which you're just not going to get for large-scale matrices using a nearest neighbors or statistical learning more generally approach. Okay, so just asking ChatGPT is not going to be the answer. Okay, we have to figure out how to break up the problem into small enough pieces that statistical learning is going to work on each of those pieces. Okay, so more broadly, right? Unreliability, right? The fact that you sort of can't trust LLM outputs. This is a problem in many domains. This is absolutely not specific to optimization, right? It's true for code generation. It's true for information retrieval and summarization. And it's true for like mathematics, if you're trying to get LLMs to generate proofs of new theorems, for example. But I would emphasize the key attribute when you're thinking about how hard or easy it's going to be to develop an LLM-based solution to each of these problems is whether the output can be reliably and cheaply checked. Okay, so the cheapest way to check is using traditional code. And that's effective, for example, for checking mathematical proofs, right? We have theorem-proving languages, and if you ask the LLM to express the proof of the theorem in a theorem-proving language like Lean 4, then you can just run code to check if the proof is correct. Okay, so that's wonderful, because if the proof is not correct, you can tell the LLM it wasn't correct, and you could continue this cycle. So you can imagine training this or fine-tuning it using like a reinforcement learning approach to actually converge to a correct solution. Okay, this is obviously a computational challenge, okay, but it's not like a conceptual challenge at that point, right? Which is kind of amazing. Okay, so I would consider something where we can check the answer with traditional code to be a ultimately a solvable problem. Okay. On the other hand, maybe you can't check it with traditional code, but maybe you could imagine checking it with a large language model. You could say, large language model, does this formulation of the problem match the original business problem that was expressed in this text? Okay. Now, it might be, right? It might, in that case, you could ask it, right? But you still have the same unreliability problem. You can say, ultimately at the end of the day, you need to know that the LLM output is something you can trust. Okay. There have been approaches to handle this difficulty. One really obvious approach is a debiasing approach. So you can estimate the error rate of the LLM check on your output by using a very sparse amount of human feedback, human checks on the output. Okay, so you could use that to estimate the error rate and then correct for it. There's a paper called Post-Prediction Inference by Michael Jordan's group that was published in Science. I think not, either Nature or Science. Anyway, that suggests doing exactly this, but it's a very straightforward idea. Just estimate the bias and then correct for the bias. Okay, but humans, right? Human checking output, that's extremely expensive. I will tell you, I'm working on a project right now with a collaborator, Ido Drury, and we're looking at the quality of LLM generated reviews of papers. Okay. And in order to assess the quality of LLM reviews of papers, we need humans to rate the reviews of papers, right? So this is essentially like the area chair role in a computer science conference. Okay. So the authors of the paper are, doing some work to assess the output so we can get statistics on this. It is so painful. It is very painful to assess the quality of LLM reviews. It's a hard job. So it's not easy, even for, human experts who could do it, it's actually extremely hard to collect sort of enough data that you can get anything like reliable statistics on this kind of question. And the larger and more complex the problem is, the harder it is for humans to check this, right? So there's a, thriving field inside human-computer interaction that thinks about, how to, for example, best use the abilities of crowdsource workers to have them sort of check small parts of a problem so that you don't overload their cognitive capacity. Because these are, if we're asking these AIs to do hard tasks, then it means that even checking the correctness is also a hard task, right? So I think that this is a real obstacle to sort of trustworthy and reliable outputs of these AI augmented systems is even, you can't provide feedback to the system or use reinforcement learning to improve it unless you can assess the quality of the outputs, and that's hard. Okay, so our goal here is going to be to use as much as possible the unique attributes of optimization to enable error checking and reduce errors. Okay, so what are the main challenges to solve these real-world optimization problems? Things that we'll see are ambiguous representations, so maybe different words used to represent the same thing. Very long problem descriptions. So for example, there's a link right here, but I think I'm not going to click on it for you, to a 60-page long paper describing a single mixed integer linear programming problem that appeared in an energy systems like power systems application. Okay, so in this paper, there is a table of parameters that is 7 pages long. Okay, with like the, ramp rate of this thing, ramp rate of that thing, ramp rate limit of this thing, ramp rate limit of that thing, maximum capacity of this thing, maximum capacity of that thing. Like, it just goes on and on and on, right? So you need to be able to have some system that doesn't get confused when you have this much information going on. Now, I would argue that this is a task you should expect a computer to be better at than a human, ultimately, right? So it's a little bit funny if we say, oh, well, the problem, it's such a large and complex problem that, the computers are never going to be better than humans. That's a crazy argument given the low working memory capacity of human brains compared to, high RAM, that's quite reliable on computers, right? So if we figure out how to do the trade-off between this like mushy part, statistical learning part, LLM part, and traditional computing, we should be able to solve that problem and solve it better than we can using human brains. I mean, human brains that they're also augmented with memory, right? Like in order to solve a problem, you and I would use paper, right? Or possibly like a Google Doc or, maybe, code or markdown or something, right? We don't try to keep all the information in our head. We can't, right? And the LLM shouldn't have to either. Okay. Large data matrices. So we would certainly want to be able to allow LLMs to solve problems with like very large data. Those are the ones that are going to sort of generate the most value. And then, of course, unreliable outputs and hallucination. You don't want it to just come up with its own constraint instead of really looking at the constraint that was present in the problem. Okay, they can also introduce really subtle errors, like the code runs, but the result is incorrect, or it might ignore a constraint, or it might have a variable that doesn't match the desired interpretation. So for example, I've seen it introduce a variable called abs price, but if you look through the constraints it's implemented, there's no constraint that guarantees that abs price is equal to the absolute value of the variable called price. Okay. You have to be pretty careful of this kind of thing. Okay. So let me describe a potential architecture that could solve these problems. And this is the architecture that we implemented in, I guess, our second version of the tool that we call OptiMUS, optimization modeling using solvers is the MUS. Okay. And you can find the code for it and also links to our paper and to our web app where you can sort of experiment with an interactive interface from our GitHub. Okay, so here's the basic architecture. Is a problem description comes in. This is just natural language. We do a little bit of pre-processing to get an initial state that I'll describe on the next slide. Okay, and this is sort of a persistent description of the problem that you should think about as living in sort of traditional code, so not something that gets forgotten about. Okay. At each step, then there's a manager agent, which is an LLM agent. That means that basically it's a prompt. It's basically just a prompt. Okay, so this manager is a prompt together with access to the initial state, and you ask it to some question like which agent should this state be sent to next in order to improve the outcome. Right, or in order to improve the fidelity to the original problem. And the manager chooses to send it either to a formulator agent, which is another LLM agent, right? Just think of it as a prompt, okay? And the formulator, what we're asking the formulator for is we're asking it to translate the problem description into like a LaTeX description, something that you might see written down in a paper as a description of a mixed integer linear program, okay? The manager can also choose to send it to a programmer who is going to change the LaTeX description into Gurobi code, okay, or some other modeling language if you prefer. And the manager can also choose to send it to an evaluator who will run the code and observe any errors that are produced by Python and pass it back to the manager. This is a pretty simple system, right? So for example, you might formulate the problem, then program all the constraints into code, then run the code, you observe an error, you send it back to the manager looks at the error and says, oh, this might be an issue that the formulator will have to address, sends it back to the formulator can improve the formulation, then it's coded again, then it's evaluated again, etc. Right? Okay, and the parameter data is held separately. So you can imagine that all of the parameter data is in some, SQL database somewhere. And, it's called by the solver. It's not called, the parameter data is not used in the modeling step. Okay, and we believe this separation is very important to allow us to solve arbitrarily large scale problems because we keep the LLM from knowing anything about the values of these parameters, which could be extremely large. Okay, at the end of the day, the evaluator runs it, an answer comes out, and the manager can pass that answer back to you and say, the revenue is whatever. Okay, so what's this state? Okay, and this is, I think, the sort of the critical sort of structure that's the innovation of our paper, which is, how do you represent the optimization problem so you can really keep track of all the parts and not lose things, right? And not lose things, not hallucinate things. Okay, so here's what we do. We process this description into first a list of all the parameters in the problem with their dimensions and a natural language description of what they represent, the objective of the problem. So this pre-processing is also done by a large language model, by the way. Okay, we say, what is the objective of the problem, right? Give me some background about the problem, and then a list of all the constraints, okay, in natural language. Okay. So once I have this, I've got everything about the problem except the variables, basically. Okay, so now here's what I'm going to do, is I'm going to go through each of the clauses in the optimization problem one by one. That means the objective and each of the constraints. And I'm going to think about what parameters and what variables this clause depends on. So as an example, the constraint for each material, the amount used should not exceed the available capacity. That depends on the material requirement. It depends on the material capacity. And it depends on a variable, which is like the production amount of that material. Okay. Okay. So if that variable doesn't exist yet, you create the LLM sort of creates that variable, provides a definition, provides a dimension for the variable, and then continues through this list of constraints. Okay, so at the end of the day, you have this graph that tells you which parameters and which variables participate in any given constraint. That's useful because it means that if you turned out to be wrong about one of the parameters or one of the variables or one of the constraints, the set of things you have to change is limited, right? So it introduces the ability to sort of edit the problem without changing the whole thing. It also allows OptiMUS to scale. It doesn't require sort of arbitrarily long context sizes in order to process arbitrarily long optimization problems. There have been a variety of other approaches for how to use AI tools in order to model and solve optimization problems. So I just want to survey sort of some of the broader class of the ideas that people have had. One really simple idea is just ask the LLM for a solution. Okay, so you don't call a solver, you just ask the LLM to solve the problem and output, a number or a vector solution. Okay. One example of this is in the NL for opt competition, where they had very simple problems, and so this approach works decently. Another example is a paper called Large Language Models as Optimizers, which is from a group at Google, and first author was Chengrun Yang, who was a former PhD student from my group. And he proposes a system that allows you to optimize your prompts in order to produce sort of better and better outputs to the optimization problem directly by the LLM. So he uses the LLM to improve the prompts given to the LLM in order to produce higher and higher quality solutions to your optimization problem. Okay. But again, it's not something that scales to large problems, and you shouldn't expect it to scale just because of the way that large language models are trained. You could ask the large language model to write its own solver sort of directly in Python code rather than calling a solver. There was a paper called Fun Search that explores this approach. Again, you shouldn't expect it to work for like very complex problems because, because it's hard to sort of directly write a solver. There's just not enough examples of solvers. And I don't expect that approach to work, at least not anytime soon. In fact, most of the best solvers are closed source, right? Especially in mixed integer linear programming. So you don't expect that these large language models are going to know enough to be able to write a good one, ever. You could ask the LLM to call a solver. And the first work that I'm sort of aware, which was of doing this, which was concurrent with our first work on OptiMUS, is called Chain of Experts. The idea is a little bit similar to what I showed you. They have a wider variety of agents, LLM agents. They, that work together to solve the problem. They don't have the structured representation of the optimization problem that OptiMUS has. Okay. But I will compare to this numerically in a moment. And then there's some work on chatbots for optimization. For example, talking to an LLM agent that helps you figure out how to fix infeasibility of your problem, or do what-if analysis and say, what if I, eliminated the supplier? What if I increased this capacity? How would my solution change? Or sort of explaining why the solution to the problem is what it is. And then there's also a modeling chatbot that was developed by Alibaba Cloud that's pretty intriguing. So lots of interest in this area. Okay. So let me show you some results of OptiMUS. And so in order to do that, okay, now we have to get into the, now we're, in the CS conference mindset, and the way that you assess quality of some research contribution in the CS conference mindset is you need a benchmark of problems and you need a baseline, right? And then you need to show that your new thing beats the baseline on the benchmark, okay? So let me describe what is the benchmark. Okay, so we've got three benchmark data sets for optimization modeling. The first is NL for opt, which has, it comes from a NeurIPS competition in 2022. It has relatively short problems, like 518 characters. They also tend to be pretty easy. There are a lot of instances in this data set. It was a real sort of achievement to put it together, but they're all linear programming problems, not mixed integer linear programming problems, which means that the set of formulation tricks is actually pretty limited. Like linear programs are actually like pretty easy to formulate. There's a lot more tricks that come up when it comes to mixed integer. Okay. Things like sort of logical constraints. Complex OR is slightly more complex. It has 12 problems that involve binary or integer variables. The lengths are still about the same. but they do tend to be a little bit more sophisticated problems that require some thoughtfulness to model. This was introduced by the Chain of Experts paper that's at iClear this year. And then there's NLP for LP, which was a data set that we collected and curated. It has 13 mixed interlinear programming problems. This is something that we're working on augmenting right now. And the problems tend to be much longer. Okay, so we collected much longer problems that we think are sort of more complex and more realistic. Okay. So the models that we'll compare, one is sort of standard, which is we just ask sort of one command, and we ask the large language model to emit code to produce the solution. Okay, so there's no structure to this. You just say, give me code to solve the problem. That solves already half of the problems in this easy data set, but a very small fraction of the ones in these harder data sets. Now, if you ask it to do something like chain of thought, right, to think step by step, the solve rate goes up a little bit. Actually, I mean, it doubles the solve rate on complex OR, increases the other one sort of marginally. Okay. Chain of Experts, which is this work at iClear 2024, improves substantially here, less substantially here. So in other words, it doesn't seem to be scaling as well to larger data sets, to longer problems. Okay. Whereas our work, it improves uniformly on Chain of Experts, and particularly on this problem of longer data sets, it's getting a really substantial boost. Okay. So it's the best. It beats the state of the art by a large margin across many different data sets. So, I guess that's good if you want to get into CS conferences. On the other hand, would you call this reliable? Would you use this, right, to make decisions in your Fortune 500 corporation? Like, absolutely not, right? These rates are absolutely not high enough to put them into production. Okay, so let's think a little bit more about what's driving these successes and these errors, and how we could, how we could fix them or improve the system, or create a system that's trustworthy and reliable. Okay? So here's an ablation study. We can try OptiMUS with different large language models as backends. So the baseline OptiMUS is built with GPT-4. You can also remove the ability to debug. In other words, remove the ability to go back after the evaluator notices a bug. That reduces the solve rate considerably on these harder data sets. On the easiest data set, doesn't worsen things by much because most of the problems are solved immediately anyway. If you replace the manager with a less powerful model, then the performance gets worse, but like not by a lot. On the other hand, if you replace all the agents, including the formulator and the programmer, with this less powerful model, the performance goes down by a ton. Okay, so this is presents an important lesson that actually it's easier. It's less harmful. Okay, you don't need as much LLM intelligence in order to reproduce the manager. Whereas the individual contributors really do need a fair amount of knowledge and power. It's kind of an interesting lesson for like the future of work, that actually the higher level the higher levels of management may be easier to replace with large language models than the lower levels of management. I don't know if you've okay, it depends on sort of what roles you've played in editorial processes, but I'm now sitting on a couple of editorial boards, and I'm like a senior area chair for certain CS conferences. And I noticed this myself, right? That my role as, for example, senior area chair, it's only to check whether the area chair's comment matches their recommendation. Does it look justified, right? I don't need to go in and actually understand the paper and do all the hard work that the reviewers do, right? To really summarize and sort of pull out the critical meat, right? I'm like a summary machine. In other words, I'm a text processor, right? And that's very easy to replace even with a simple LLM. Okay, and I think something similar is true here. Like, much easier to figure out who you should send the next, which worker should you call on, than it is to actually do the work. Okay. Okay, ablation study on number of agent calls. This is the question, like, is it actually helping that we allow OptiMUS to pass the problem back to previous experts, right? So if you could only call 3 agents, right, that would mean you would first formulate the problem, then program the problem, then evaluate the problem, done. Okay. And if you only allow this, you can still solve most of the problems on the easy data set, but the harder data sets, your performance is really much lower. Okay. If you allow yourself to call more and more agents, okay, the performance keeps improving up to about 8 agent calls. Okay. So we really are improving by being able to sort of observe the errors and revise our answer in response. Okay. On the other hand, here's a different view. This is the average number of calls to each agent among the problems that were solved correctly. Okay. So what does that look like? On this easy data set, NL for opt, basically you call the formulator once, the programmer once, the evaluator once, done. Okay. On the hard data set, here's a more typical trajectory. You call the formulator once, then you call the programmer, then you call the evaluator, error. So then you call the programmer again to fix the error. You call the evaluator again to fix the error, done. Okay, you can see this from the fact that the average number of calls is 2. Okay, there's some variance, so sometimes you make 3 calls, okay, but you almost never go back to the formulator. You can see among the solved problems, right, this is very, very close to 1 with pretty low variance. Okay, so it's very rare that we revisit the formulator to improve the formulation and solve a problem that we would not be able to solve with one formulation. Okay. So that's obviously a place for future improvement. And that's something that we're actively working on. Okay, so when OptiMUS fails, why? It can be due to incorrect modeling. It's often due to missing constraints, particularly on the easy data set. And it's sometimes due to coding errors as well. So the coding errors, I expect that to just improve itself as these LLM-based systems get more powerful. Incorrect modeling or missing constraints, I think that these are going to be more persistent problems that are something that's appropriate for optimizers to think about who are interested in modeling languages. Okay, so qualitatively, what's going on with generating these errors? What we see is the LLMs often oversimplify, like they might omit components of objectives or constraints. They might struggle with certain problem types, like we see them struggling with time-dependent behavior. Like you can do, like if you take this action now, then in the next time period, you can do the following, and in the time period after that, you can do something else. Okay, this is sort of complex logical, but also time-dependent behavior. Or in graph problems like multi-commodity flow. Okay, it also doesn't do great at modeling those. Okay, we also see minor variations in the input prompts leading to very different models. This is something that people at these AI companies are actively working on, but we have observed that adding please can improve the solve rate from 20% to 80% on some problems, not on other problems. Okay. Here's one case study on currency exchange. So given n currencies and their exchange rates, suppose you want to maximize the money transferred to currency 1 subject to transfer limits on each currency pair. You ask OptiMUS to solve this problem and it says, yeah, I just maximize the sum over all the currencies of the conversion rate between currency I and currency 1 times the amount converted from currency I to currency 1. Okay. But if you create this model, the solver is going to find a sort of hack of a solution, which is that it creates loops. It transfers from currency 1 back to the other currency and then back to currency 1 again. Okay. So it's not the right model for the problem because you should not be allowed to do this. Okay. You can prevent loops with a net transfer objective, right? It should be the net amount transferred from currency I to currency 1 minus the amount transferred from currency 1 to currency I. Okay, or you could constrain the solution never to transfer out of currency 1. Okay. So this is the kind of constraint that the LLM might miss. Okay, here's another study in production planning. So you could say in each year T, workers can either produce new products to sell in year T+1, or they can increase factory size, and that new factory comes online in year T+2. Okay. So this is also kind of problem that leads to sort of for some reason the LLM makes mistakes with this. Frankly, I think people probably would too, which is that GPT, but we observe really different mistakes from different models. So GPT-4 identifies all the constraints, but it forgets the time lag, okay? Whereas Claude 3 gets the time lag right, but it allocates workers to multiple jobs simultaneously. Okay, so the fact that we're observing different errors from different models, I think that's just a sign that that there's room for improvement. But the fact that between both models together, they would get it right, it means that this is the kind of thing that we expect LLMs to be fine at, right? This is sort of a this is a growing pain, but I don't expect this to be a persistent issue for LLM-based modeling of optimization. Okay. So we don't see LLMs sort of correctly solving the entire thing all at once. So it's clear that we should think about ways to allow LLMs to interact with humans in order to improve their ability to solve optimization. Okay, so we built an interactive optimization modeling system just as a, as a proof of concept. And I'll show you a little bit about how that works. So here's an example problem. It's a production planning problem. You say, given a number of products, each product produces at a specific rate. We've got a certain number of hours in a week. A ton of each product results in a known profit. Got a lower and upper limit on how much of that product you can sell in a week. You want to maximize total profit. How do you decide how much of each product to produce? Okay, it's a very basic production planning problem. Let's try it in our web app. Okay, so here's the first step is you put in a description like that in the description tab, and here's what comes out. The first step is that OptiMUS identifies which things in the problem description are parameters, right, for which you should have an associated data file and numerical data. So it says, so it replaces the number of products. It calls that a parameter called P. It says the specific rate it's going to call production rate. It defines hours available, which is how many hours are available in a week. Okay, and you can see each of these is then put on this list of parameters, the dimension, and it fills in the definition of what that parameter represents. Okay, so I would say this is already really cool. Okay, next step. You say, let's extract the constraints and the objective. Okay, and so it finds the objective, says some background on the problem, and a list of constraints. Now I want to point out this second constraint. The production volume for each product must be an integer value if products cannot be fractionally produced. Like, that's true, but it's not a constraint. In fact, it's a tautology. Okay. So you can delete that, trash that constraint. Okay. But actually, the fact that this kind of thing is an issue means that many of the failures for OptiMUS, they're not like important failures. They're like, it's getting the spirit of the problem right? This is getting the spirit of the problem right. It's just not going to be able to actually solve the problem if it has this in there. It's going to result in some kind of error. There's another constraint we should look at. The production of each product is constrained by its respective production rate in tons per hour. Is that a constraint? Not really. It's the definition of the parameter production rate. Okay, so again, trash that constraint, not a constraint. Okay. Now this is interesting. So now we go to coding. So we say formulation. Formulation is going from the natural language description to something that looks like LaTeX. Okay. So you can formulate all these problems, and this is interesting. This constraint in natural language said non-negative production constraint for each blah 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 for each product. But the formulation says tons sold is greater than or equal to a lower limit. Lower limit was not even referred to within the natural language input here. Okay, so the LLM is hallucinating the fact that this constraint should depend on the lower limit. Okay, so again, this is kind of interesting. That's a pretty appropriate, this is a reasonable constraint. In fact, it is the constraint that appears next. Okay, but it's not faithful to this particular description. Okay, so I would call this a hallucination, but it's not a bad hallucination. Okay, next step, you upload a data file, and OptiMUS will even generate a synthetic data file if you don't have one that you know that you care about. And then you can solve it. You say run the code, and it'll say, oh, there's an error, invalid data in vars array, blah, 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 blah. So then you click fix code. Haven't you always wanted this button? Fix code. Okay, it fixes the code. You run it again and the run is successful. Okay, and it outputs, you should sell 3 tons of the first product and 3 tons of the second. Great. Okay, so this is all well and good, but it's sort of far away from the kinds of things that the optimizers hold dear, like solving optimization problems faster, right? Like improving your formulation in order to solve the optimization problem faster. That's something that's a little closer to the mathematics that we all know and love. Okay, let me think about whether we can teach large language models these optimization formulation tricks that allow us to scale our models to larger problems. So how would we do this, right? Well, the first thing we might do is say, well, what are the tricks that we know? And you might even be able to enumerate them. I would say this idea came out in a conversation that I had with Wotao Yin. So I'm going to attribute it to him, that the list of all optimization tricks is innumerable. Okay, so we started trying to enumerate them. And in our first version, we iteratively prompted OptiMUS to consider each one. Now we just have a prompt that says, which of these tricks do you think might be appropriate for this problem? Okay, so here's an example. You could say, I have an optimization problem. Here's the description, and then here's the formulation. Okay. And now, if I've decided to consider total unimodularity, I say, well, there's a type of mixed integer linear programming problem that satisfies total unimodularity, and this is what that means. Now, would you say that this problem is totally unimodular, right? If so, please update the formulation, update the code accordingly. Okay, and it can do this. Okay, here's an example. Here's an example problem. Let's say Stanford plans to build new dining halls on campus. It costs alpha j times c to build a dining hall of capacity c at each candidate location. Let's say we've got a bunch of I different residences on campus, each of which houses ni students. And we've got a constraint that we're not going to build more than 1 dining hall in North Campus and no more than 1 in South Campus. Your goal is to minimize the distance from the students to their food plus the building cost. So let's think about this constraint. Okay, how would you represent the constraint that you can build at most 1 dining hall on South Campus? Okay, pretty typically, you would have a variable ck to represent the capacity at each location k, which will be 0 if it's not built. So you know that of the CKs that pertain to South Campus, no more than 1 of them can be non-zero. Okay, so how do you represent this as a mixed integer linear program? Usually here's what you'd do. You'd introduce another auxiliary variable, xk, which would be binary. You'd have the sum of the xk's on South Campus be less than or equal to 1. Okay, and so if it's binary and they add up to less than or equal to 1, that means exactly 1 is 1, all the rest are 0. And then you constrain ck to be less than or equal to some large number m times xk. Okay, that's called a big M relaxation. Okay. There's another way that you can tell Gurobi about the structure. Okay, so here we're taking advantage of the fact that if Gurobi understands that you have this structure, that only 1 of the CKs can be non-zero, all the rest are 0. Right? If you tell it explicitly about the structure, it can make better choices inside its branch and bound routine and actually solve the problem more efficiently. Okay, so this is called a special ordered set. And you can just tell Gurobi these CKs form a special ordered set, right? SOS1, which means at most 1 can be non-zero. So let's try this out. We generate 2 codes using OptiMUS. The first one is just the standard one that OptiMUS forms. And the second one, we tell it to consider the special ordered set technique and then use the model it produces after doing this. Okay. And so we've got 2 codes. And we generate a bunch of synthetic data problems of different sizes, and we see how well each of these solves these problems. Okay, so we see that the standard formulation, the mixed integer linear program, it gets slower and slower and slower as the number of locations increases. Whereas with the SOS formulation, it scales more gracefully to larger problem sizes. Okay. So in other words, prompting LLMs to consider these advanced techniques really does help produce scalable models. Awesome. So what have we seen, right? We've seen some challenges and we've seen some solutions, right? we've seen long problem descriptions, big data matrices, hallucination, and bad models, and we can solve these, okay? So for long problem descriptions, what did we do? We decomposed the problem into the structured representation. Another possible approach is just bigger context windows. It's not clear whether this decomposition will remain important as context windows grow. I rather think it will, but time will tell. Big data matrices, the solution is to use a solver. Hallucination, the solution is testing, okay? And a careful division of labor between testing using LLMs and testing using sort of human input. And for bad models, the solution is education, okay? Tell the LLM about the formulation tricks and it can do them. Okay, I want to take a couple of moments to talk about sort of broader implications or sort of broader sort of connections of this work to bigger topics in AI. One is optimization and AI safety. Many people, when you think about apocalyptic scenarios for an AI getting out of control and doing the wrong thing, many of the scenarios involve a misspecified optimization objective. Okay, so for example, there's this classic thought experiment from Nick Bostrom, who's a philosopher at Oxford, about a paperclip maximizer, that you have an AI superintelligence that you put in charge of your paperclip factory, and you say, AI superintelligence, I want you to make as many paperclips as possible, right? Thinking that that's the way that you'll maximize the profit of your factory. But in fact, what would an AI superintelligence that's connected to robots and, mechanisms do with this command? I don't know, maybe it would try to figure out how to harness all of the energy and all of the material on Earth in order to make paper clips, destroying all life on Earth as a byproduct, right? So it's clearly not what you wanted, okay? So I would say this just raises the perspective that specifying our optimization problems correctly and really making sure that the AI and human understand what each other wants and what each other means is really, really critical, right? So thinking about, so I would connect sort of OptiMUS to this broader mission. Making sure that we know how to ask for what we want is going to be a more and more important skill as AI gets more powerful. Second, I want to connect this to like AI in the future of work, right? Like what, are we replacing people? Are we talking about replacing optimization experts and putting people out of work? And I would say that's not what we're talking about. So this is from a paper by 3 economists asking, can we have pro-worker AI? And they say, well, AI can reduce inequality if it enables lower ranked workers to perform more valuable work. And because so many of the routine tasks that workers previously performed have already been automated, a large fraction of current jobs require non-routine problem solving to decision-making tasks. Okay, and this is like, exactly the domain that optimization targets, right? Empowering workers to perform these tasks more effectively, for example, using these AI tools that we're developing, and to accomplish even more sophisticated decision-making tasks, right? Maybe making better decisions because it's easier for them to access these, sophisticated solvers, right? Will require providing workers with better information and decision support tools, okay? So this is exactly the mission that I see us as supporting as we develop tools like OptiMUS, is really helping people improve their capacity for decision-making and problem solving, and really, improving the kinds of efficiency and overall quality that we can deliver throughout our economy. Okay, the big question here, for my own research, maybe, if you're interested also for yours, right? What are the limits of large language models for optimization? I can tell you about some future directions I think are really exciting. One is robust optimization, using the AI to help expand the imaginative capacity of the modeler for what might go wrong and scenarios that you should really be trying to insure against with your decisions. So for example, if you're doing airline scheduling, you should really think about what happens if there's a problem at one airport or problem at another airport. What happens if there's a weather system that impacts the Midwest or a weather system that impacts the West, or earthquake, or whatever it is, right? These are sometimes, I think the reason that they're often not often the reason why people don't adopt a robust optimization perspective and solve sort of what I would consider the right problem, right? Maximizing, your performance, at the sort of 10th percentile or sort of even under risk, is that it's hard to generate these scenarios, like to even figure out like what you should be concerned about changing and how might it change. And this is something that LLMs are great at, right? Then we're using really the imaginative capacity of the LLMs and their generative capacity rather than like the correctness, which is not so great, right? So I think this is a really exciting direction. Synthesizing small data sets to check model correctness. This is something that OR researchers in industry do all the time. And it's often hard to figure out like what's the right small data set. Automatically choosing a solver or heuristic to meet timer accuracy requirements. Learning constraints from user feedback. Explaining and improving the existing model. So acting like a chatbot to explain the model to you. Of course, there's no reason to constrain these kinds of ideas to mixed integer linear programming. You can imagine doing this for many other kinds of optimization problem or beyond optimization for stochastic simulation problems. I think this would be really powerful. Certainly, there's room to improve modeling using LLM tricks. We're exploring retrieval augmented generation right now. So looking up sort of similar problems and how those were solved in order to improve the formulation. I'm also really excited about the possibility for vague optimization, right? For being able to, help you formulate problems where you don't necessarily have data, or you're not even sure about what your constraints or objective are, and having the LLM help walk you through what your goals might be. Okay? So I would love to hear your questions, and thanks for your attention.